Hello again, my name is Tom Irvine, and I'm the instructor for this series of shock and vibration webinar units. And once again, I'd like to thank Dr. Curtis Larson and the NASA Engineering and Safety Center, NESC, for making this series of webinars possible. Today we're going to be covering digital filtering, and as an added bonus, we're also going to take a look at some seismology as well. And it might seem kind of odd to study seismology in a presentation sponsored by NASA, but let's just think for a minute. Suppose there's a payload on a Delta II rocket that's being launched out of Vandenberg, California. Well, that launch vehicle and its payload mounted on the pad at Vandenberg have to withstand potential earthquake excitation from the San Andreas Fault, which is nearby. So this rocket and its payload is this tall cantilever beam subjected to base excitation, and analysis is required accordingly for potential earthquake events. Plus, it's good just to have some cross-training as well. So filtering is a tool for resolving signals, and filtering can be performed on either the analog or digital signal. Well, today we're just going to be focusing mainly on digital signals, but I do want to mention a little bit about analog filters. And filters can be used for a number of purposes. So let's say we have an analog signal from an accelerometer or some other sensor. As a good engineering practice, we would route that signal through an analog low-pass filter prior to the analog to digital conversion. And the reason we would do that is to prevent an error source called an aliasing error. And this is an error whereby the high frequency energy, spectral components in other words, are folded about the Nyquist frequency and deposited at the lower frequencies, thus giving the appearance that the energy at lower frequencies is higher than it really is. Well, in a previous webinar unit, we went over Nyquist frequencies and sample rates and aliasing, so I'll let you refer back to the previous unit to get more information on that. But I will say quickly that the cutoff frequency for the analog low-pass filter should be less than 1/2 of the sample rate frequency. And again, specific rules of thumb are available in the previous webinar unit that discussed sampling the Nyquist frequencies and aliasing. So another purpose that we could have for filtering, and this will be now for digital filtering, is we may wish to clarify the resonant behavior within a signal by attenuating the energy at frequencies away from that resonance. That could be a bandpass filter, for example. We'll talk about bandpass filtering here shortly. Let's see. So we're going to cover some practical applications and example in this unit, and we're going to be talking about a time domain filter, which is a digital Butterworth filter. Or I should say we're going to be discussing how to implement a digital Butterworth filter in the time domain. And we are going to do this using a digital recursive equation. And in order to do that, we need to derive the filter coefficients, and we have to consider Laplace transforms and partial fraction expansion and Z transforms. And I've got a paper on my blog that goes through all those steps that you can read at your leisure as a homework assignment. Okay, so there's different ways we can characterize filters. There are some filters that are high-pass filters and others that are low-pass filters, for example. So a high-pass filter is a filter which allows the high-frequency energy to pass through, and it is thus used to remove or attenuate the low-frequency energy from the signal. And conversely, a low-pass filter is a filter which allows the low-frequency energy to pass through, and it attenuates the high-frequency energy from a signal. Now we can also construct a bandpass filter by using a high-pass filter and a low-pass filter in series, and we'll do that later on. Now we can also characterize the filters in terms of the filter type, and a Butterworth filter is one of several common infinite impulse response or IIR filters. And this group also includes Bessel and Chebyshev filters. And these filters have feedback loops, and that's important for stability. And the Butterworth filter can be used for either high pass, low pass, or band pass filtering. And it is characterized by its cutoff frequency. And the cutoff frequency for a Butterworth filter is the frequency at which the corresponding transfer function magnitude is minus 3 dB, which is equivalent to a magnitude scale of 0.707. We'll take a look at the transfer functions here shortly. Now, a Butterworth filter is also characterized by its order. And a 6-order Butterworth filter is the filter that we're going to be using in this webinar unit. And it's a good all-around general purpose filter. Now, one of the properties of these Butterworth filters is that the transfer magnitude is minus 3 dB at the cutoff frequency regardless of the order. But other types of filters such as Bessel do not share this characteristic. And we'll look at some transfer functions for Butterworth filters in an upcoming slide, or slides I should say. But let's start. Let's look at a low-pass filter. It's going to be a 6-order Butterworth filter, and it will have a cutoff frequency of 100 Hertz. Let's take a look at its transfer function. So this transfer function here, it's a magnitude and phase plot. And there's two subplots, and as you can see, they're both functions of frequency in Hertz along their respective x-axes. The upper one is, well, first I should duly note, Butterworth low-pass filter, 6-order, FC means cutoff frequency equals 100 Hertz. And one of our concerns with this filter is that the phase angle varies with frequency. And then about 85 Hertz or so, thereabouts, well, let's make that 75 Hertz, okay, about 75 Hertz or so, there's a sort of a wraparound effect that occurs. So if we plot from minus 180 to 180 degrees, there's a jump that occurs. But we have some concern about that phase, the potential phase distortion that's going to occur. If we have some steady state stationary broadband random vibration signal and we're filtering it, phase distortion is probably okay. But if we have a transient signal, then the phase distortion could be a problem. Now, we're going to find we're going to cover, I should say, cover a method for correcting for phase distortion. That'll be in an upcoming slide. Let's take a look at the magnitude here for this 100 Hertz low pass filter. So we start off with a unity gain, and that unity gain goes out to somewhere around 75 to 80 Hertz. We see a roll-off effect start to occur. So here's the roll-off, and then this cutoff frequency point, which is at 100 Hertz, has a magnitude of minus 3 dB, which is equivalent to 0.707. Now, an ideal filter would be just a flat plateau, clear out to 100 Hertz, with a shear wall vertical drop-off. And wouldn't that be ideal? Well, it turns out if we try and construct that filter, we get numerical instability, and that's just a fancy way for saying that our filtered signal would just blow up. We get some crazy high values. So we have to, for practical purposes, accept this limitation, and the consequence is we're going to filter out some of the energy close to 100 Hertz, or I should say leading up to 100 Hertz. We're going to sacrifice a little bit of that energy, and we're going to retain some of the energy above 100 Hertz. Well, just keep in mind also that this is a log-log plot. So this would look different, obviously, if it's linear. Now, again, this is a 6-order filter. Well, if we went to higher order, then this plateau would extend a little further before the drop-off, and the drop-off would be a sharper slope. Well, the problem is, as we go to higher and higher orders, we're more likely to encounter numerical instability. So I like to use 6-order just as a good general purpose filter. Okay, let's go to the MATLAB GUI package here. So let me just type in vibration data to call up our GUI package. And we're up to version 5.3 and rising. So we're going to have a time domain input, time history input. And we're going to go to filters various. We'll begin our signal analysis. And we're going to do a Butterworth filter. Now, this script applies a 6-order Butterworth filter to a time history. The input array must have 2 columns, time in seconds and amplitude. Well, even before we call in our time history, we can do a few extra things with this particular function here, and we can display what the transfer function is. So I'm going to put in 100 hertz. This will be a low-pass filter. For now, we'll do no phase correction. We will cover phase correction shortly, but not right now. So let's no, we're not going to calculate the response. That would be for a time domain input. Let's display the transfer function. Okay, we get a couple of plots that show up here. Well, actually a pair of plots. This first plot is the transfer function in terms of real and imaginary components. And we're not going to be so interested in this one here. Rather, we're going to look at the equivalent magnitude and phase. Well, the equivalent magnitude and phase, you've already seen this on the PowerPoint slide, but I'm just showing you how I calculated those curves so that if you ever want to put in your own filter parameters, you can calculate what that transfer function would be. So let's just minimize this for now, and we'll park this off to the side. Well, let's don't park it off to the side quite yet. Let's do a 100 hertz high pass filter. So again, Butterworth 6-order, 100 hertz, high pass filter, phase correction no. Let's display the transfer function. Okay, the real and imaginary we're going to ignore. Okay, here's what we get. It's the same transfer function as before, except instead of low pass, now we have high pass. But the cutoff frequency remains 100 hertz, and this is a 6-order filter. So in this case, you can see we have this sort of a ramp effect that occurs. Then the ramp kind of rolls into a plateau there. So we are going to retain a portion of the energy below 100 hertz. And we are going to attenuate a slight amount of energy above 100 hertz. But again, due to the practical considerations of numerical stability, this is what we need to do. That's what we're going to do anyways. Okay, let's do one other. Let's do a bandpass filter. So this is going to be a high-pass filter and a low-pass filter in series. Let's go from 100 to 200 hertz. That difference there is a 1-octave step. Okay, let's ignore real and imaginary, and let's just go to the magnitude and phase here. So Butterworth bandpass filter, 6-order, 100 to 200 hertz. Well, ideally, I guess you'd call this the pass band. Ideally, within the pass band from 100 to 200 hertz, there would be a flat plateau with unity gain. But again, we have some practical considerations. So we do retain some energy below 100 hertz. We do attenuate some energy there slightly above 100 hertz, and similarly for the 200 hertz case. And we do still have some phase distortion effects going on. Well, for practical purposes, this is what we would do, the transfer function we would have if we were trying to filter between 100 and 200 hertz. And the numbers we enter here did not necessarily have to be a 1-octave separation. I just did that I guess I thought it'd be a good case to look at for convenience. Okay, this plot here, this is actually a Butterworth low-pass filter, and the cutoff frequency for convenience is set to 1 radians per second. And this is showing 3 different orders. So the L equals the order. So we could have the blue curve here that's a second order. The red curve is a fourth order. And then the black curve is a sixth order. So again, each of these three curves, regardless of order, passes through the same minus 3 dB point at the cutoff frequency. And you can also see that by increasing the order, we come closer to meeting the ideal of an ideal filter, which would have a flat plateau out to 100 Hertz and then a shear wall drop off. But the trade-off, and I have not demonstrated this to you, but just for now, I guess take my word for it. The higher we increase the order and the closer we meet the ideal filter, the more likely we are to have numerical instability. And you'll find that when we actually get around to filtering a signal using the MATLAB GUI package, the vibration data GUI package, one of the outputs that will appear in the command window is an assessment of the filter stability. Okay, so you might think, okay, we have those transfer functions in the frequency domain, either the magnitude and phase or the equivalent real and imaginary. So how about if we take the Fourier transform of the input time history, we'll multiply that input Fourier transform by the filter transfer function in its complex form. Then we'll take the resultant Fourier transform and we'll take its inverse, and that will give us our filtered time history in the time domain. And that would actually be a valid approach, but we don't use it for a couple of reasons. One is the time domain method is more computationally efficient. And also when we go about doing our Fourier transforms, there are some error sources that we could encounter, like a leakage error, for example. So that's why those are some of the reasons we favor doing this filtering in the time domain. So what we're going to do is, let's say we take our transfer function and we'll represent it by h as a function of omega. So imagine taking the time domain equivalent of that transfer function, which will be a digital recursive filtering relationship. And we're going to take x sub k, that's our input time domain signal, and go through the digital recursive filtering process, and then we'll get our output signal in the time domain. So this is what we need to do. And to do that, we're going to come up with a filtering equation. Well, here's our implementation of our digital recursive filtering relationship. So let's allow x to be our input time history, and y will be our output time history, and k will be a time index. So what we're going to have is this formula here is shown on the right. Now, in these curly brackets here, there are two sets of terms. So the first set of terms, and L is the filter order. So we have B sub n. These are the coefficients that get multiplied against the time history input points, and then there's the summation is shown here. And in order to calculate those coefficients, we need to refer to the methods that I have on a paper posted on my blog for this webinar unit. Now the second term we have minus, and then the second term here, this is the recursion part of the filtering. So the A sub n are the coefficients for the recursive term. So recursion is just a fancy way of saying that the response at any given time point depends in part on the responses at previous time points. And this is the feedback loop. This is why our filter is going to be an infinite impulse response filter. And that feedback loop is desirable for stability. Now, ideally, a filter should provide linear phase response. And this is particularly desirable if we have a transient signal or if we're doing a shock response spectrum calculation. Well, the problem, as we've seen, is that Butterworth filters do not have a linear phase response. And other infinite impulse response filters share this problem. However, there are a number of methods available to correct the phase response. And the method I'm going to show you is something I would have never thought of on my own. But it works, and it's very innovative, so I credit whoever invented this. And what we're going to do is take our time history and we're going to play it backwards. So we're going to reverse our time history. And if this were a live course I was teaching, I'd make some jokes about encoded messages in popular music and rock songs like Stairway to Heaven or Beatles' Abbey Road, if Paul is dead or something like that. But anyways, you get the idea. Some of you are probably too young to know about that music. So anyways, we reverse the time history. We play it into our digital recursive filtering relationship, which is the time domain equivalent of the transfer function. Now this intermediate output time history, we reverse it. So now the time history is pointing in the correct direction, and then we filter it one more time. So we call this refiltering for phase correction. Now a consequence of this is that it changes the response at the cutoff frequency from minus 3 dB to minus 6 dB. Well, let's see how that works. So I'm going to go back to our GUI package here, go to Butterworth filter, and let's do something we've done before. We've already done a 100 Hertz low pass filter, but this time I'm going to turn on the refiltering for phase correction. So let's take a look here. Okay. Okay, plot 4 is just showing the real and imaginary. Well, the blue curve is the real, and the imaginary is the green, but the imaginary component goes to 0. And I should mention this is the amplitude versus frequency in Hertz. Now here's the same transfer function, but in terms of magnitude and phase. In this case, the phase angle is 0 across all the frequencies. Our magnitude is shown here. We have unity gain. Then we have a roll-off. Well, this minus 3 dB point, which was minus 0, well, which was 0.707 before, has now dropped to 0.5, which is minus 6 dB. So that's what happens when we refilter for phase correction for our Butterworth filter. Okay, so well, this slide just essentially shows what I demonstrated in MATLAB. Butterworth low-pass filter, 6-order, refiltering, cutoff frequency 100 Hertz, phase angle, magnitude. Each is a function of frequency in Hertz. And here you can see at 100 Hertz, this curve is going through the point at 0.5, which is the minus 6 dB point. Okay, now we're going to have some fun. And if this were a live course, I would ask my students, okay, does everyone here have a work-related hobby? So if you're an electrical engineer, do you also have your ham radio license? Or if you're working in the aerospace industry, do you fly remote control planes or go out and launch model rockets or something like that? So at one time, I built a homemade seismometer and recorded some earthquake data. And we're going to play around with this data, and it's kind of a fun way to explore filtering. So the flag there is from the Solomon Islands, and there was an earthquake, magnitude 6.8, that occurred near the Solomon Islands on October 8th, 2004. That's about 10 years ago. And I measured this data using my homemade seismometer, and at the time I was living in Mesa, Arizona. Well, now I'm living in Madison, Alabama, close to Huntsville, but that's where I lived. And I was able to record this data. And I was particularly interested in finding the onset of the P wave, which is the primary wave, within that seismic data. In order to do that, I had to do some filtering. So I'm going to just show you a couple slides here of what this seismometer looked like. And it's called a Lehman seismometer. And Lehman is the name of a gentleman who published a diagram and for this type of seismometer, actually built one himself, and recorded some data, and then in a scientific type magazine or journal, he presented his results. Well, I suppose if you go online, you can find some company that will sell you a Lehman seismometer. But kind of the spirit of a Lehman seismometer is you just go out to the garage and you just scrounge around with odds and ends pieces of hardware, and you make your own. So that's the true spirit. And my machinery abilities are very rudimentary, but somehow I was able to cobble together one of these seismometers. And having said that, I had few, if any, very few of these parts already in my garage. I made numerous trips to the hardware store and ordered parts from McMaster Car to make one of these. But anyways, it operates like a horizontal swinging gate. So this is a horizontal pendulum boom. And the idea is that the pendulum boom remains stationary in its own inertial space while the ground below is shaking. And then there's a sensor that then measures the relative displacement from the sensor itself to a little metallic target that's on the boom. I'll show you some additional slides. This will become much more clear. But just a few highlights here. There's a chisel blade here that butts up against a chrome polished bolt, and that's the pivot point. Then there's a wire rope cable that comes down from this frame with a little turnbuckle to adjust the tension. And then there's a ballast mass here that's partially submerged in a pan of oil to provide damping. Okay, here is the sensor, and this is a non-contact displacement transducer. So there's actually an air gap from the sensor head to this metallic target. And the sensor, it does not measure absolute displacement. Rather, it measures relative displacement. And I did not have this calibrated in any particular unit, so the results that I obtained were unscaled relative displacement. And I think this is some kind of a linear variable induction transducer or some such thing. I actually ordered it from the Omega company. And here is just another view. You can see the sensor here with its little air gap and the metallic target. And then here's the ballast mass made from lead, partially submerged in this pan of oil. And I've got a few other miscellaneous pieces of hardware hanging off this. And that was because I went through a whole iteration of various transducers before I could find one that would give good results. And in fact, the classic Lehman seismometer would actually have a electromagnetic coil that would vibrate or oscillate back and forth between the poles of a magnet, and then the resulting current in that coil would be proportional to velocity of the coil. Well, I tried that and I could not get it to work, but I was able to use this relative displacement sensor and get some good readings. So I was happy. Here is the chisel blade, and it butts up against the chrome polished bolt. Okay, now this is not an earthquake. This is unscaled relative displacement, so the fact that you see plus and minus 5 there doesn't mean anything. But this is relative displacement versus time, and what I did is I gave the pendulum boom an initial displacement and then let it undergo free vibration. Now, this is not a perfect single degree of freedom response, but if with a little bit of imagination, we'll say that yes, this is a single degree of freedom response. And the frequency was so low that it's more convenient to represent it in terms of the equivalent period, which is 14.2 seconds. And then the damping was 9.8%. And that's a good damping value. And the period of 14.2 seconds is reasonable. An ideal period would be much longer. But the problem is with this whole setup is that this is very delicate and required a great deal of tender, loving care, and due to all sorts of things, due to changes in room temperature, due to ground vibration from cars driving out in the street, or footfall vibration within the home, or who knows, all different other sources. This pendulum had a tendency to swing either to the right or to the left till it reached a hard stop. In fact, this little frame here was designed to stop the pendulum boom, but between certain relative displacement limits. Well, again, this thing required daily adjustment, and if I had made if I had constructed this so it had a longer period, then it would have become even more likely to become unstable. So there's a trade-off between stability and period, and I suppose if I had this in some underground bunker, kept at a constant pressure, constant temperature, isolated from, well, we can't isolate it, can we? But if I had it in a more idealized room or something like that, then it would have had better performance. But this was good enough. So here's the data acquisition system I had. Beautiful system. It was made by Nicolay, and Nicolay has been bought and sold, and I think that company really doesn't exist anymore, and its product line has been discontinued. But there's another company called High Techniques that's picked up their engineers and technology that has a similar system available. And this is the first earthquake I recorded, and it was from that Solomon Islands earthquake. And you can see the time history there, the yellow time history on the screen of that Nicolay system. And here is, I'll call this the raw data. So this is the Lehman seismometer, the horizontal response to the Solomon Island earthquake. Date and time duly noted. We have the relative displacement along the y-axis, time in seconds along the x-axis. And the seismic wave has various components to it. The P wave, the primary wave. The S wave, also known as the secondary or shear wave. The LQ is the love wave, and then there's also a Rayleigh wave. And there's also different forms. What you have to remember or know about these waveforms is that some of these waves propagate through the center of the Earth, through the body of the Earth. Other waveforms propagate along the surface of the Earth. And as those waveforms, particularly the body waves, reflect and refract across the various layers of the Earth, one type of waveform may transform into another type of waveform. And it gets very complicated in some of these later arriving waveforms, that they may be a waveform that's undergone 3 or 4 or 5 or 6 different transformations. Well, I adjusted this data, or I wanted to adjust it. My goal was to adjust it so that the earthquake occurred at time 0 at the Solomon Islands. Now, in order for the P wave to travel from the Solomon Islands to my home in Mesa, Arizona, that required about 700 or 800 seconds worth of time. And I was able to calculate that using some online tools provided by the U.S. Geological Survey. But if you look at this data, you'd see, well, the onset of that S wave is quite clear. But the onset of that P wave is kind of ambiguous. And you can see there's quite a bit of noise occurring before that P wave. In fact, just looking at this, it's hard to say that this little bulge is really a P wave at all. Well, why is there noise? Well, obviously there's some instrumentation noise. That's inevitable. But we also have to remember that the Earth itself is always vibrating. It's in a state of constant vibration, seismic vibration, but the vast majority of this vibration is imperceptible to the human senses. And that daily vibration, it occurs for various reasons. There's the gravitational interactions between the sun, the earth, and the moon. There are tidal effects. There's winds. There are mid-oceanic ridges where there's an upwelling of magma that's driving tectonic plates. So the earth is always vibrating. And that's why you can see some vibration occurring before that P wave was to arrive at my home in Mesa, Arizona. So I had to be sure that there really was a P wave. And I went through some trial and error process. And let me just, let's just do this in MATLAB here. This is good practice. So we're going to take a time history and we're going to filter it. We're going to have a Butterworth filter. And we're going to call up the data. It's going to be an external ASCII file. This is available at my blog. It's sm.txt. Y-axis unscaled relative displacement. We're actually going to do a high-pass filter. Let's do 0.2 hertz. Since this is a transient signal, or we're looking for a transient signal, let's go ahead and use our phase correction, our refiltering for phase correction. Let's just go ahead and calculate the response. So we have unscaled relative displacement versus time in seconds. And if we high-pass filter at 0.2 hertz, we can see there is a distinct onset of that P wave. And that gives us confidence that we have adjusted the time scale so that time 0 is the time that the earthquake actually occurred. That's when it originated. And then the P wave took 700 seconds, or well, it's about 750 seconds or so to reach my home in Mesa, Arizona. Okay, so this is actually the input data here. So this is the S wave, the distinct the distinct transit, that's the S wave. And this little bulge here was the P wave, but by high-pass filtering, we were able to determine that that just wasn't any ordinary bulge. It was, in fact, the onset of the P wave. So let's see. Let's get back to our slides here, and then this is the same filtered results. And I've applied the letters P and S there to show the two different waveforms. Now, I had this seismometer set up, and it really required a lot of tender, loving care, as I mentioned. It took a lot of fine-tuning and adjustment. And I was able to capture maybe about 4 or so earthquakes. So I was pretty happy with myself, and at that point the system went offline because I got busy with other things. Well, what happened when I took my system offline? Well, that's when the big one hit. The 2004, the Sumatra earthquake hit, the Indonesian, Malaysia, and that part of the world, and it generated tsunamis that sadly killed quite a few people. So I missed the big one, just like a fisherman's story there. Just some information. We can divide seismic waves into 2 different types. There's body waves and surface waves. And the body waves have a shorter period with a higher natural frequency. The surface waves have a longer period with a shorter natural frequency. And that comes from a seismology textbook. And actually, as I'm scratching my head here, natural frequency implies maybe the response of a structure, so I'm not sure if natural is the correct adjective or not. Maybe I should have just said frequency here. I have to think about that a bit. Now, I've been talking about P waves, so you're probably wondering, what is a P wave? And the best way to think of a P wave is structural born sound. So the structural born sound wave propagates, and there are alternate bands of compression and, well, I'm just going to say the stretching. I don't know how to pronounce that word. So we get this compression and stretching as the waveform propagates along. So think about it like a slinky, taking a slinky in your hands, and if you could hold it horizontally, and you're moving, say from right to left or left to right, and you have that slinky stretched a bit, and you're exciting it uh, so that the alternate the stretching and compression occurs. Now another characteristic about these P waves is that they can go through air, they can go through water, liquids, they can go through granite or solid material. And it's also the fastest of the four common waveforms. That's why it's the first one that we're looking for, the first one to arrive at my home seismology station. So that's the P wave. Then the S wave or shear wave, or S could be for secondary wave. It's another type of body wave, and in this case, you see that the displacement is occurring perpendicular to the direction of propagation. So the S wave produces an amplitude disturbance that is at right angles to the direction of propagation. Now, water cannot support a shear force, and this is a shearing action. So S waves do not propagate through water. And that's actually very advantageous for seismologists, because if a major earthquake happens in say, China, that can be recorded by seismic stations in the United States or anywhere else in the world. And seismologists use these seismic body waves to essentially X-ray the Earth. And what they've concluded is that the Earth must have a partially molten core, because those P waves can propagate right through that core, but the S waves cannot. So the S wave energy just reflects off that core. So that's maybe the major reason, or at least one of several reasons, that geologists have concluded that the Earth has a partially molten core, I guess made up of some iron and nickel. Now the love wave is a shearing horizontal wave, and it propagates along the surface of the Earth, and it cannot go through water, so it can only go through solid material. So that's the love wave. Nothing to do with romance. Love was the name of a seismologist who characterized these waveforms. Then we have the Rayleigh wave. Now, a Rayleigh wave is also a surface wave, and it can go through either land or sea. And it's very much like an ocean wave. Just think of a rolling ocean wave coming into shore. But unlike the ocean wave, this motion is retrograde. So we have these counterclockwise spinning circles as the waveform propagates. Whereas with an ocean wave, we would have a prograde waveform. So we'd have a clockwise rotation as we propagate from left to right. So that's kind of an interesting effect. One of the things I ask my students in the live course is, if you're an earthquake engineer and you have to design a tall building to withstand an earthquake, or if you have to, if you're concerned about a Delta II or some other launch vehicle going out of Vandenberg that has to withstand an earthquake while it's during that 2-week period while it's on the launch pad. So if you're in either of those two scenarios, which of these two waveforms are you most concerned with? P wave, shear wave, love wave, or Rayleigh wave? Well, it turns out it's the two surface waves, the two waves that propagate along the surface of the Earth, that can cause the most potential damage to a tall building or launch vehicle. So imagine a tall cantilever beam here. So this love wave would shake that cantilever beam in the axis that's perpendicular to this slide. Or you could say the axis that's out of plane with this slide. The love wave, now imagine a tall cantilever beam mounted on to the ground, and a Rayleigh wave comes along. Well, that's going to cause that tall cantilever beam to have a vibration that's in plane with this slide. So it's the love wave and the Rayleigh wave that are of most concern to earthquake engineers. So what we've done so far in this unit is we've talked about filters, and we threw in some seismology because it's a good way to learn about filtering in terms of filtering as a practical application. And let's go ahead and just finish off by okay, so let's finish off by going to vibration data. So let's go to vibration data, blog, and let's just type in filtering here in the search box. So webinar 19, that's the one we've just covered. And I've got the PowerPoint slides there, the data file for the Solomon Island earthquake. And then here's a reference paper. And this has the explanation of the derivation of those filtering coefficients that are needed to perform the filtering. And I just thought of one other thing that I meant to show you earlier, I should say. When we filter, when we use our MATLAB GUI script to use our Butterworth 6-order filter, there's some printouts here. And usually these won't really be very important to you, but they could be. There's the A coefficients, the B coefficients. And then I have some information about stability. And for this particular case, we had 3 stages. We had good stability for each of the 3 stages. So our output filtered signal was a stable signal. So sometimes you might see, if you have a borderline case, you might see marginally stable or marginally unstable, or you might see something that's completely unstable. And that has to do with the sample rate, the Nyquist frequency, and the filtering, the cutoff frequency. And just as a quick little guideline, anytime we select our filtering frequencies, they should be less than the Nyquist frequency. And the Nyquist frequency is 1/2 the sample rate. So that about wraps it up for this unit. We're actually going to cover digital filtering in the next unit as well, because there are some other uses of it for it. So I hope you've enjoyed this unit, and we'll talk to you later. So thank you and goodbye.